When most people think about what powers a ship, they picture one thing: a massive engine deep in the hull, turning a propeller, pushing the vessel forward. That mental model is not wrong, but it is dangerously incomplete because almost every large commercial ship operating today is not powered by one system. It is powered by two entirely separate, independently operated power systems that share almost no components, draw from separate fuel supplies, and are designed so that the complete failure of one cannot disable the other. One system drives the ship, the other one runs everything else and keeps the crew alive when the first one stops. Most people have never heard of the second system. And that is exactly the problem, because understanding why it exists tells you something fundamental about how ships are actually designed, what naval engineers consider their worst case scenario, and why redundancy in maritime engineering is not a luxury, but a survival requirement. To understand why two separate power systems exist, you first need to understand what happens when a ship loses all electrical power at sea. The event has a name: a blackout, not a partial failure, not a reduced capacity situation, a complete, total loss of generated electrical power across the entire vessel. When a blackout occurs on a large ship at sea, the consequences cascade immediately and in a specific order. The main propulsion system loses power. The ship begins to decelerate and within minutes loses steerage, the ability to control its heading. Without steerage, a ship in open ocean drifts. In confined waters, near coastlines, in shipping lanes, or approaching port, drifting means collision risk. Simultaneously, navigation systems go dark. Radar, GPS, electronic chart displays, communication equipment. All of it requires electrical power. The engine control room loses its monitoring systems. Pumps that manage ballast, fuel transfer, cooling water, and builds drainage stop operating. Ventilation in enclosed spaces shuts down. Fire detection and suppression systems lose power. Emergency lighting fails. In a matter of minutes, a vessel that was operating normally becomes a dark, drifting, increasingly dangerous environment with no propulsion, no navigation, no communication, and no active safety systems. This is not a theoretical scenario. Blackouts happen on commercial vessels. They have caused groundings, collisions, and loss of life. The engineering response to this risk is the reason every large ship carries a second, completely independent power generation system, and why that system is physically separated from the main one. The primary power system on a large commercial ship centers on the main engine, almost always a large two-stroke diesel engine in the case of cargo ships and tankers. These engines are among the largest reciprocating machines ever built. The Wärtsilä RT-Flex 96C, one of the largest marine diesel engines in production, is 13.5 meters tall, 26.6 meters long, and produces up to 80,080 kilowatts of shaft power, roughly 107,000 horsepower. It weighs approximately 2,300 metric tons on its own. The cylinder bore, the diameter of each individual piston, is 960 millimeters, nearly 1 meter across. This engine turns the propeller shaft directly or through a reduction gearbox, driving the vessel forward. In most modern large ships, the main engine also drives shaft generators. Electrical generators mechanically connected to the propulsion shaft, which produce a significant portion of the ship's electrical power while underway. But the main engine is optimized for one thing: producing forward thrust at sea. It operates at relatively fixed speeds, it takes time to start and stop, and it is not designed to serve as a flexible, responsive electrical power source for the ship's systems. That is the job of the auxiliary engine room. The auxiliary engine room, sometimes called the generator room or the alternator room depending on the vessel, is a separate compartment, typically located either above or forward of the main engine room, housing a set of medium-speed four-stroke diesel generators. These are not small units. On a large container ship, each auxiliary generator may produce between 2,000 and 5,000 kilowatts of electrical power. A vessel of that size typically carries 3 to 5 of these generators, any combination of which can be operated simultaneously depending on the ship's electrical load at a given time. In port, where the main engine is shut down and the shaft generators produce nothing, the auxiliary generators provide all electrical power: lighting, cargo handling cranes, refrigerated container power, air conditioning, navigation systems, communication equipment, pumps, and every other electrically powered system on the ship. At sea, the auxiliary generators supplement the shaft generators, handling peak loads and maintaining supply when the main engine speed fluctuates during maneuvers. The auxiliary engine room runs continuously on its own schedule, managed independently from the main engine. It has its own fuel supply lines, its own cooling systems, its own control panels, and its own ventilation. A problem in the main engine room does not automatically affect the auxiliary engine room, and that separation is entirely intentional. But even this separation is not the final layer. Beneath both systems, required by international maritime law under the SOLAS Convention, the International Convention for the Safety of Life at Sea, every ship above a certain size must carry a third, entirely independent emergency power source. This is the emergency generator, and it represents the absolute last line of electrical defense on the vessel. The emergency generator is housed in a dedicated space that is not the main engine room and not the auxiliary engine room. It is positioned as high in the ship as structurally practical, typically on an upper deck or in a deck house, specifically so that flooding of the lower hull, which might disable both main and auxiliary systems, cannot reach it. The emergency generator must be capable of starting automatically within 45 seconds of a main power failure without any human intervention. It runs on its own separate fuel tank, which must contain enough fuel to run continuously for a minimum of 18 hours under the International Maritime Organization's requirements, though many ships carry significantly more. The emergency generator does not power the entire ship. It powers only the systems that are absolutely critical for survival and navigation. Emergency lighting throughout the ship, the fire detection and alarm system, the fire pump, the bilge pump, the navigation lights, the radio communication equipment, the steering gear, and the engine room ventilation fans needed to restart the main generators. Everything else remains dark, but the critical systems stay alive, and the crew retains the ability to communicate, navigate, and begin recovery procedures. The physical separation of these three systems is not just a regulatory formality. It reflects a specific engineering philosophy that maritime designers call defense in depth. The principle that no single failure event should be capable of disabling all layers of a safety critical system simultaneously. A fire in the main engine room is catastrophic for propulsion, but the emergency generator on the upper deck is unaffected. A flooding event in the lower hull can destroy the main and auxiliary engine rooms, but the high-mounted emergency generator continues operating. A fuel contamination problem that disables the auxiliary generators cannot reach the emergency generator's separate dedicated tank. Each layer is designed to fail independently so that the failure of any one layer does not propagate to the others. This same philosophy governs the routing of electrical cables on a ship. Critical systems are fed by two separate cable runs that follow different physical paths through the hull, one on the port side, one on the starboard side, so that a fire, flooding, or structural damage in one section of the ship cannot sever both power feeds to the same critical equipment simultaneously. The management of electrical load across these systems is itself a complex engineering task. At any given moment, the ship's electrical load changes. Cargo refrigeration units cycling on and off, deck machinery starting and stopping, weather conditions changing the demand on climate systems. The power management system, a dedicated computer that monitors and controls the electrical plant, constantly balances load across the operating generators, automatically starts additional generators when load increases beyond a threshold, and sheds non-critical loads if a generator trips offline unexpectedly to prevent the surge of unmet demand from cascading into a full blackout. This automatic load management is one of the most important safety systems on a modern ship, and its failure mode is carefully designed to default to the safest possible state rather than the most convenient one. A generator that trips offline triggers automatic load shedding before the remaining generators overload and trip as well, because losing one generator and shedding some load is manageable, while losing all generators simultaneously is the blackout scenario that every layer of the system is designed to prevent. The vulnerability of this entire architecture is most visible during a specific operational phase, maneuvering in port. When a ship approaches a port, the main engine transitions from steady sea-speed operation to variable speed maneuvering mode. Accelerating, decelerating, reversing, responding to tugboat assistance and pilot commands. During this phase, shaft generators are often disconnected because their output frequency varies with engine speed, which is incompatible with the stable frequency required by the ship's electrical systems. The full electrical load transfers to the auxiliary generators. Simultaneously, the maneuvering demands on the main engine are at their highest. Bow thrusters and stern thrusters are consuming large amounts of electrical power, and the margin for any electrical failure is at its smallest. This is why port maneuvering is the phase during which blackout incidents are statistically most likely. Naval engineers designed the power transition from sea mode to port mode as a carefully sequenced procedure, with the auxiliary generators fully loaded and confirmed stable before the shaft generators are disconnected, and with the emergency generator confirmed ready throughout. The sequence is not discretionary. It is a required procedure because the consequences of getting it wrong in a confined harbor are immediate and potentially catastrophic. The operational demands on the auxiliary engine room also extend well beyond electrical generation. On many vessels, the auxiliary engines drive not just generators, but also large compressors for refrigerated cargo systems, hydraulic power units for deck machinery, and air compressors for control systems. The thermal energy from the auxiliary engine exhaust is recovered by waste heat boilers that produce steam for fuel heating, cargo heating, and accommodation services. The auxiliary engine room is, in many respects, the most continuously active space on the ship. Running in port, running at sea, running during cargo operations, running during maintenance periods on the main engine. While the main engine may be shut down for inspection, maintenance, or port operations for days at a time, the auxiliary generators run around the clock. stopping only briefly one at a time for their own scheduled maintenance while the others take the load. So when you stand at a dock and watch a large ship sitting at berth, engines apparently quiet, no visible movement, no propeller turning, understand that inside that hull, at least one and probably two auxiliary diesel generators are running continuously, producing thousands of kilowatts of electrical power, maintaining every system on the vessel in operational readiness. And somewhere higher in the ship, in a room most crew members hope they never need to rely on, the emergency generator sits on standby, fuel tank full, automatic start system armed, waiting for the event that every layer of engineering before it was designed to prevent. A ship is not a machine with one engine. It is a system with three independent layers of power generation, each one designed to work when the others fail, each one isolated from the others so that no single event can take all three down simultaneously. That architecture, invisible, unglamorous, never discussed in the same breath as horsepower or speed records, is what keeps a ship operational and its crew alive when everything else goes wrong. And that raises a question about what happens when the main propulsion system itself fails completely at sea. Not just a blackout, but a full mechanical breakdown of the main engine with no port nearby and no repair capability on board. How do ships manage propulsion emergencies in open ocean? The answer involves a system most passengers and observers never know exists, and the engineering logic behind it is as counterintuitive as everything else we have looked at on this channel.